Thanks for joining me in my virtual talk. My name is Sharon Perrone, and I'm a PhD candidate at the University of Minnesota. I'll be talking today about my work on dynamic soil health indicators in southern Minnesota. My research story starts here. In September 2018, the Natural Resources Conservation Service submitted this notice to the Federal Register announcing intent to publish a technical note endorsing dynamic soil health indicators and associated methodologies. The technical note came out shortly thereafter. In order to validate these indicators, a project was initiated to develop a national data set across various soil types and management systems under the direction of Dr. Skye Wills in the National Lab in Lincoln, Nebraska. So the research that I'm going to be presenting today is from one of these projects. In order for a soil health indicator and method to make the list, they should meet 4 specific criteria. The first one is that they should be effective. So the indicator should be able to distinguish between different forms of management and should be sensitive over the course of 1 to 3 years. So if a producer is trying something new in the field, the indicator should be able to detect a change in 1 to 3 years. Second, these indicators should be production ready. They should utilize equipment that are frequently found in laboratories across the country. They should be high throughput, and they should be cost effective. They should also be repeatable, so if different labs across the country have the same samples, you should get very similar answers. And finally, these indicators should be interpretable, meaning that there is some sort of directionality to their interpretation, either on a more is better scale or a less is better scale, or potentially there might be some central optimum. Now, you've heard me use the phrase dynamic soil properties a few times now, and for this presentation, we use it to refer to properties that change with time on a human timescale. They are assessed to measure and predict soil change with land use management. So this gets back to that efficacy criteria and distinguishes that these properties differ from static soil properties, which represent things such as texture and mineralogy. And if you're into Twitter, you can use the hashtag DSP4SH. So there's a rich world on Twitter there waiting for you. With that understanding, the broad objective of my research is to determine the ability of dynamic soil properties to distinguish among management practices under static soil and environmental conditions. The management systems that we were including in this study include 2 agricultural treatments with nearly a century of colonial agricultural history and 1 reference treatment. The first treatment is what we are calling a conventional treatment, characterized by a corn-soy rotation, regular spring tillage at 4 inches and fall tillage at 12 inches, and standard herbicide and fungicide inputs. The alternative treatment has a more variable rotation, which includes corn, soy, cereal rye, oats, and crimson clover, and has only been tilled once in 6 years to a depth of 3 inches. And further, this alternative treatment has not received any fertility inputs outside of crop residue in the past 6 years. Finally, the reference site is a never been tilled fence row at the southern edge of the conventional section and is meant to represent the soil in its original state, although that's sort of an ideal situation. In our case, the fence row was vegetated with giant ragweed, stinging nettle, and brome grass, and contained a significant cap of silty surface deposition, most likely from the wind erosion off the conventional field over many years of cultivation. This study took place in Mower County, Minnesota, which is highlighted in the red in the map of Minnesota in the top right corner. This land that I'm working on is on the traditional and contemporary home of the Anishinaabe people and what would have been right on the border of tallgrass prairie and oak savanna. It was really critical for this project to find contrasting treatments that were located on soils sharing the same soil forming factors. So in this case, we found 2 different management systems that were adjacent to each other, and what you see as mapped as M511A, which corresponds to a reedland silt loam. At the time of the study, both fields were in soybean. In each treatment, we sampled 3 replicates, and each replicate consisted of 3 separate pedons made up of 3 to 5 composite cores. So each treatment had 9 pedons for a total of 27 pedons, and each pedon was subsampled by genetic horizon to 100 centimeters. Cores were pulled with a hydraulic Giddings probe seen here after soybean harvest in October and November of 2019. We collected an extensive field data set, but today I'll mainly be focusing on pedon descriptions. We are also in the process of analyzing an extensive set of recommended soil health indicators, which is really the focus of this talk today, listed in that NRCS technical note. And today I will be speaking specifically about bulk density, autoclave citrate extractable protein, and permanganate oxidizable carbon. Bulk density is a commonly used metric to assess soil compaction and opportunities for gas exchange and water percolation. It operates on a less is better scale, modeled here, with less dense soils being considered favorable. Some considerations impacting the use of bulk density as a good candidate indicator is its temporal variability during the growing season, its analytical variability by method, and the potential difficulty of adjusting interpretations based on rock fragments and soil texture. Finally, it's also very labor intensive, especially for trying to reach those lower depths. The second indicator is autoclave citrate extractable protein, or ACE protein, which operates on a more is better scale. The concept is that nitrogen bound up in proteins can be quantified as a potential source of mineral N. This method is a more recent soil health indicator, having previously been thought to extract glomalin-related protein only, but has since been found to be more promiscuous in its protein response. And because of this, it has not yet been thoroughly tested as a soil health indicator. And indeed, it's shown some mixed results in terms of its ability to distinguish between management systems. Further, it may be a worse predictor of organic N mineralization than the simple metric of total soil nitrogen. Finally, we review permanganate oxidizable carbon, or POXC, which also operates on a more is better scale. POXC is thought to represent an active fraction of carbon that serves as a microbial substrate, which is ultimately a proxy for microbiotic food availability. However, this method has been found to be highly variable across labs and according to soil processing, and may in fact actually simply represent an incomplete oxidation of total soil carbon. However, POXC has been found to distinguish between management systems in several studies. So now I'll get into some of my results, and I'll start with my pedon descriptions. We ultimately found 3 tax adjunct soil series for our 27 pedons. They are shown here in order, with Reedland being in the low edge drainage class and Kenyan being in the high edge drainage class of 3. Together, these series represent almost 1 million acres of farmland in southeastern Minnesota and northeastern Iowa. Here, I've used the R-Package Algorithms for Quantitative Pedology, or AQP, to visualize my 27 pedons. The conventional and alternative treatments were a mixture of Reedland and Marquis silt loams, while the reference treatment was solely Kenyan due to that thick surface deposition that I mentioned earlier. Next, I looked at bulk density. Here you see bulk density as a function of depth, and density increasing along the x-axis, and depth starting at the soil surface and going down to 1 meter on the y-axis. The blue color represents the alternative treatment, the green is conventional, and the red is the reference soil. From this graph, you can see that the reference site has a lower bulk density than the agricultural treatments at all depths. What's of interest to me, though, is the difference between the 2 agricultural treatments. I worked with Dylan Bodette at the California Soil Resource Lab to develop a function that iterates a pairwise contrast over each soil centimeter. The results of this contrast between the 2 agricultural treatments can be seen in the blue and gray bar on the left-hand side of the graph, where blue represents differences between the treatments at alpha equals 0.05, and gray represents no differences. Here, we see that the alternative treatment had a higher bulk density than the conventional treatment from 5 to 25 centimeters, and again from 61 to 87 centimeters. This is somewhat discouraging, as we like to think of these soil health practices as improving bulk density, but it does also corroborate several studies that show how no-till can increase compaction in the short term during that period of conversion. Next, I display the results here from ACE protein. Again, we have the alternative treatment in blue, the conventional treatment in green, and the reference in red, with soil depth on the y-axis. Again, the reference has higher protein than the agricultural treatments at all depths, but if we look at the pairwise contrast between the agricultural treatments, we see that the alternative treatment has higher ACE protein at 0 to 5 centimeters and again at 32 to 35 centimeters. And although technically the conventional treatment is higher than the alternative at 77 to 80 centimeters, I would refrain from making an inference about this due to the fact that both treatments are approaching 0 and have very narrow confidence intervals at these depths. Finally, the results of our POXC study show the reference treatment as generally being higher than the agricultural treatments, although similar in the 5 to 20 centimeter range, while the pairwise contrast between the conventional and alternative treatments shows the only difference at 32 to 35 centimeters, where alternative was higher than conventional. In conclusion, we found a range of drainage classes that differ from the map projections. The reference treatment differed from the agricultural treatments at all depths and all metrics measured. So we are able to distinguish some differences between soils under similar static soil formation conditions. The alternative treatment increased bulk density at some depths. POXC was largely the same for both agricultural treatments, and the alternative treatment had higher ACE protein than the conventional treatment at 0 to 5 centimeters and again at 32 to 35 centimeters. I will be really interested to see how these patterns persist or contrast with other soil health metrics and look forward to connecting with you about some of my future results. I also do foresee many opportunities for this data to be utilized in different ways. So firstly, as I continue to work with this data, I plan to use generalized least squares and linear mixed models to assess depth dependency of these dynamic soil properties, which I hope will be more robust than the sort of iterative pairwise comparison by centimeter that I just shared with all of you. Secondly, I'd really love to dig into the broader data set from soils around the country and start to understand connections between these dynamic soil properties and more static soil properties such as mineralogy and hydrology. With that, I'd be remiss if I didn't thank everyone who has contributed to this research, and I thank you personally for attending my presentation today. So please feel free to reach out to me at the above email address if you'd like to follow up, and I hope you have a great rest of your day. Thank you.